Welcome to this video course on optoelectronic materials and devices. Optoelectronics, as is well known, is one of the most exciting areas in electronics as well as material science. In the last 20 years, there have been dramatic developments in the field, and in this course I will try and attempt to describe and discuss some of the most important developments. There are a number of very important applications of optoelectronics in systems, which I'll also discuss as I go along. For example, we know that one of the most important breakthroughs in communication has been the use of optical fibers. These are very thin glass fibers through which light travels unattenuated for hundreds of kilometers. Obviously, this requires semiconductor devices, optoelectronic sources, as well as detectors, which I will discuss and describe as I go along. The title of this course is Optoelectronic Materials and Devices, and the main topics that I'll describe in this course of 42 lectures are starting from the fundamentals of optical processes in semiconductors, because these form the active sources and detectors in most optoelectronic systems. So the first few lectures will discuss in detail the optical processes, such as I'll talk about luminescence, the emission of light, from solids. Then I'll discuss radiative versus non-radiative recombination. From luminescence, I will go into a discussion of optical absorption and the applications of optical absorption in photodetectors. This is a major field of study in optoelectronics. How to make detectors which are wideband, which are fast, highly sensitive, and also operate at room temperature. So photodetectors can be classified into two broad categories as thermal detectors and quantum detectors. I'll discuss both of these classes in detail. Thermal detectors include the very well-known thermoelectric type detectors, including thermopiles and the more modern pyroelectric detectors. The quantum detectors are the ones that have shown rapid improvement in recent times, and these include p-n junction, PIN diodes, avalanche photodiodes, and more recently resonant cavity detectors, and finally quantum well infrared photodetectors. these detectors have very interesting and novel properties. They are fast, and their detection range can go well into the infrared. After discussion of detectors, we will go on to a discussion of light or infrared emitting sources. Sources are of generally two types: light emitting diodes, LEDs, and laser diodes. We will discuss the broad principles of LEDs and laser diodes, the different types of LEDs and laser diodes. They are generally of two types. They can be surface emitting or edge emitting. LEDs, as is well known, have a large number of applications in display devices. In different electronic equipment, they are used to display digits or numbers, and they come in different colors. They come typically in red, yellow, and green. What is it that gives rise to the different colors? How can one make very efficient light emitting diodes emitting either in the red or in the yellow or the green? The green is where the light is most sensitive to the human eye, and hence there is a lot of demand for multicolor displays in which all these colors are apparent. Lasers have shown tremendous improvement in the last decade or so, and we'll be discussing in a not only homojunction type of lasers. These were the first to be discovered. Then we'll go on to a discussion of heterojunction lasers of various types based on gallium arsenide as well as indium phosphide. We'll compare the properties and the requirements of these two types of lasers. We'll talk about what determines their wavelength, the threshold current, the power output of these lasers, and we'll go on to the recent types of lasers, which include quantum well lasers, quantum wire lasers, and quantum dot lasers, vertical cavity surface emitting lasers, BC cells, and also strained layer devices. Finally, we'll talk about systems of modulation, electro-optic modulators, which are of two different categories. One is based on typical nonlinear optic materials like lithium niobate, and the other class are based on quantum well devices. all these devices are now being integrated into what are known as optoelectronic integrated circuits. This is a very important and fascinating field in which we can combine things like a detector and an amplifier on the same chip, or we can combine a laser and a modulator on the same chip. This not only gives enhanced performance, it can be easily combined and used in systems, and so we will talk about some systems applications of these optoelectronic materials and devices. I've already mentioned that one of the most important emerging areas which has already made its impact in communication is fiber optic communication. So during the course of these lectures, I'll often refer to applications in fiber optics. The question is, what sources are suitable for fiber optics? What detectors are best for fiber optic applications? How can they be made faster in the future? What further improvements are in sight? Another class of applications are for remote sensing, which also includes environmental monitoring. Optical techniques are very well suited for detection of pollution, for detection of remote objects, for imaging, and hence this is a very important and fast developing area. There are defense applications such as in night vision systems, which also employs optoelectronic devices. These systems work in the infrared. For LEDs, display devices are a very important field of application. We'll discuss that. And most recently, we have optical memories and storage devices, which also uses sources and thin films for detection of optical information. So these are the ranges of applications that we'll discuss as we go along, and we'll try and highlight some of the main features of these systems. Now, among optoelectronic materials, which forms the basis of these lectures, I will mainly concentrate on semiconductors, which form the heart of all active devices, be they sources or detectors. These are invariably made out of different types of semiconductors whose properties are crucial to the operation of the devices. Apart from semiconductors, we also have different types of ferroelectrics, or dielectrics, which are used both in detectors and modulators. To give a few examples, one of the most important ferroelectrics is lithium niobate, which is used as a substrate for integrated optics. It's also very popular for very fast modulators. So lithium niobate is one of the most important ferroelectric materials, which is transparent, birefringent, and has very low loss. Other materials of the same family are lithium tantalate, which can be used as a pyroelectric detector. Triglycine sulfate, which is also used as a pyroelectric detector. Lead zirconate titanate, which can be used as acoustoelectric detectors and surface SAW devices for SAW devices. So there's a whole family of ferroelectrics which have some importance in optoelectronics. Apart from that, we have glasses, and I will talk mainly about SiO2 based glasses, which are at the heart of optical fibers. There are also polymers, which are used for coating and passivation, both of glasses as well as for semiconductor devices. And of course, a variety of metals which are used for contacts, encapsulation, and as heat sinks. So, optoelectronic materials encompasses a whole variety of materials, the most important of which are semiconductors. Now, if we start from an elementary approach to materials based on the periodic table, we find that the most well-known semiconductor is silicon, which is in the group 4 of the periodic table. If I the whole of microelectronics is based on silicon, which is in the group 4 of the periodic table. The earlier semiconductors were germanium, but the most important from the point of view of optoelectronics are the 3,5 compounds, notably gallium arsenide, indium phosphide, and other combinations of elements in the group 3 and group 5 of the periodic table. These include the aluminium compounds, the antimonides, and some particular applications we can include the wide bandgap semiconductor boron nitride. If we enlarge this family of materials, then we include the 2,6 compounds, which are more ionic, have higher band gaps, and the principal 2,6 compounds that are of importance are zinc selenides. The 2,6 compounds are based on the zinc and cadmium families, which combine with the chalcogenides sulfur, selenium and tellurium to yield wide band gap semiconductors, which are important for devices such as blue emitting devices. You may have noticed that when I have talked about LEDs, I talked about red, yellow and green. One of the most important recent developments is the need for blue emitting LEDs and lasers, which were just not available until a few years back. What are the materials that can form these blue sources? This has been a very challenging area of development, and we'll see that gallium nitride and the family of gallium, aluminum, indium nitride has opened up a new area in optoelectronics devices which are able to produce blue emitting lasers. A rival family is based on these zinc compounds, zinc, sulfur selenides, etc. 2,6 compounds which are also in the competition to make blue devices. Now, as we know, a semiconductor is a material with a band gap between the highest filled and the lowest empty band, with a band gap given by Eg, which is measured in electron volts. And when we are talking about optoelectronics, if we think about light being incident, light with energy h nu being incident on a semiconductor, then obviously electron hole pairs are created if h nu is greater than or equal to Eg. Now h nu is hc by lambda, greater than or equal to Eg. So the most elementary and important optoelectronic property of a semiconductor is that there is a cutoff wavelength lambda, which is equal to 1.24 by Eg in electron volts. That means that only radiation with wavelengths shorter than lambda are able to excite electron hole pairs in a semiconductor, and this relation lambda c in microns is 1.24 by Eg in electron volts. I'll come back to this over and over again, but when talking about blue lasers, we know that the wavelength of blue light is roughly in the range of say 300 to 400 nanometers, or 0.3 to 0.4 microns. So what should be the band gap? The band gap of materials which emit in the blue will obviously be then 1.24 by 0.3 to 0.4. So obviously the band gap will be in the range of 4 to 3 electron volts. So this is an elementary introduction to the search for materials which have specific applications. If we are looking for semiconductors to emit in the blue, then we must go to materials which have a band gap of 3 to 4 eV. Now, let me talk about optoelectronic applications. We know that glass is a very transparent material, and we have seen that over the years, since glass was first discovered in Egypt, 3000 BC, the transparency of glass has improved tremendously over the years from 3000 BC to date. This graph plots the optical loss in dBs per kilometer with year. And until about 1966, the optical loss was of the order of 10 to the power 3, that's 1000 dB per kilometer. It was about this time that Cow and Hockham predicted that glass could be an ideal material for transmitting optical signals, and thereafter we see that the loss in optical fibers reduced dramatically from 10 to the power 3 dB per kilometer to 0.2 dB per kilometer. Now, at what wavelengths is this glass transparent? It turns out that if we look at what are these optical fibers like, it consists of a core which is about 8 to 10 microns in diameter, surrounded by a cladding which is 125 microns. And if we look at the loss versus wavelength, we find that the loss is a minimum at 1.3 and 1.55 microns. So obviously, if you want to send light long distances, we would like the sources and the detectors to operate at 1.3 microns and 1.55 microns. So what semiconductors are required? If we go back to our relation, Eg is 1.24 by lambda. If we put lambda is 1.3 microns, we find Eg is about 0.9 eV. If you put lambda is 1.55 microns, Eg is about 0.8 eV. So for fiber optic communication, we want semiconductors which will have band gaps of this region. Now, if we look at the band gaps of existing semiconductors, we will find that silicon has a band gap of 1.1 electron volts. Gallium arsenide has a band gap of 1.4 electron volts. Indium phosphide has a band gap of 1.35 electron volts. So none of these satisfy the requirement for optical fiber communication. So in the 70s, a search ensued for looking at materials which will have the required band gap. And if I just introduce the subject of semiconductors for fiber optics, this is a very important diagram which gives the band gap of semiconductors versus lattice parameter. And if you see, the band gap goes from 0.51, 1.52. And if we are looking for materials with a specific band gap, we can take the horizontal line corresponding to 0.8 and extrapolate. And we find that the most common semiconductors, gallium arsenide, indium phosphide, they do not have the specific band gap required for fiber optic communication. If we are looking for one, on this axis we have the wavelength corresponding to this band gap. So if you are looking for a emission at a wavelength of 1.5, and if we draw a horizontal line, we find that this intersects this vertical line for a given lattice parameter corresponding to a lattice parameter of indium phosphide. So we find that for fiber optic communication we have to use materials based on indium phosphide as a substrate, and if we look at this vertical line, this corresponds to materials having this quaternary composition gallium indium arsenide. This is gallium arsenide, indium phosphide, indium arsenide, and gallium phosphide. So this is within the ternary or quaternary family of indium gallium arsenide phosphide, which will lattice match to indium phosphide, and hence we find that our requirements of fiber optic communication are satisfied by the material indium 1 - X, gallium X, arsenic 1 - Y, phosphorus Y, where for 1.3 microns the composition X must be equal to 0.26, Y must be equal to 0.4, whereas for 1.55 microns X is equal to 0.4 and Y is equal to 0.1. So it is because we want emitters and sources working at these specific wavelengths 1.3 and 1.55 microns, we have to take recourse to this band gap versus lattice constant diagram to choose materials with the proper band gap and with the proper lattice constant. I'll discuss the importance of lattice constant as I go along. For growing epitaxial single crystal layers, the grown layers, the thin layers, have to have the same lattice constant as the substrates. And the substrates that are available are binary substrates such as indium phosphide, gallium arsenide, indium arsenide, etc. So all active layers are based on single crystal epitaxial layers which are grown on substrates with matching lattice parameters. Of course, recent developments have shown that we can grow strained layers with slightly different lattice parameters, but the basic thinking is that we have to take substrates such as indium phosphide and grow lattice matched or nearly lattice matched layers on this. This is an example of a very important application of optoelectronics, and overall if you look at the system, we are sending light through an optical fiber at the wavelength at which the attenuation is very small. What does the whole system consist of? It consists of a transmitter, a receiver with the optical fiber. In the transmitter we have a drive circuit where the electrical signal comes in, a light source, this is the optoelectronic device which converts electricity into light. The light sources can be of two types, laser diodes or LEDs. We'll discuss the advantages and disadvantages of them later on. This light is modulated with the information to be sent, passes through the optical fiber, travels tens or hundreds of kilometers, and it goes to the photodetector, which is again a semiconductor device. The photodetector could be a PIN diode or an APD, followed by an amplifier and signal restorer, and then we get the electrical signal out, and this constitutes a receiver. So this is the fundamental of an optical fiber transmission system, which we'll discuss. We'll talk about first the materials that go into the light sources, the materials that go into the photodetectors, and what are the performances and the responses of these light sources and photodetectors. One of the most critical devices in these transmission systems are lasers, which I'll discuss in detail. These are the older heterojunction lasers. Now we have multi-quantum well lasers and graded refractive index lasers. Just as glasses have shown remarkable improvements over the last couple of decades, semiconductor lasers have shown remarkable improvements in the last 30 years since their discovery in 1962. This is a plot of the threshold current of lasers in the last 30 years, and we'll see how over this period of time, lasers, which were very novel and rather laboratory curiosities, had currents of the order of 10 to the power 4, 10,000 amperes per centimeter squared or more. And in the last 30 years, now we have lasers in which the threshold current density has come down to about 20 amperes per centimeter squared. This is using novel techniques like multi-quantum well devices grown by molecular beam epitaxy. And so the tremendous improvements in semiconductor lasers in speed and power output and efficiency has spurred this optoelectronic revolution of the last